In pursuit of transferring technical knowledge and just to gear up the new engineering entrant, myself Pranab is here to deliver today's presentation, Power Transformer Part 77. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with generation of free charges in transformer's dielectric fluid. Transformer oil, though, has the excellent insulation property, but still there may have to contain trace amounts of free charges. Free charges in oil are being generated by several key mechanisms under various conditions, which include electrical, thermal, and mechanical stresses. The generation of free charges in transformer oil while under electrical stress would have been a complex process involving several mechanisms. One, field-dependent ionization of oil molecules. Number two, field emission from electrodes. Number three, ionic dissociation of impurities. And four, impact ionization, especially when impurities of polar contaminant like water molecules are present. Thermal stress in transformer oil that denotes an accelerated process of oil degradation and physical changes caused by prolonged exposure to the elevated temperatures, particularly in localized areas called hotspots. The generation of free charges in transformer oil while under thermal stress is primarily driven by the mechanisms stated hereunder. Thermal degradation and oxidation, especially in the presence of oxygen and moisture. Number two, ionic dissociation. Number three, increased charge mobility within the oil. Number four, charge trapping and detrapping at oil paper interfaces. Number five, generation of water molecules as a byproduct of cellulose paper degradation, causing to increase the oil's conductivity and partial discharge activity, contributing to free charge generation and movement. Mechanical stress in transformer oil that denotes the physical forces and pressures as experienced by the oil, primarily due to underneath factors. A, thermal cycles, that is expansion and contraction of windings and other components, especially due to load fluctuations and electrical fault induced forces. B, electromagnetic forces, especially during short circuits, that can lead to generate severe vibration in windings and its structural components, causing oil surges. And C, fluid flow dynamics and vibration causing to generate free charges through a process called streaming electrification. The accumulation of free charges in transformer oil is primarily caused by static electrification due to oil flow and charge injection from electrodes under high electric field. During the cooling cycle, the oil has to flow in the transformer tank around the core, windings, and isolation barriers, that is, pressboard, paper pressboard. The electrostatic charges would have to appear and accumulate at the interface of two dielectrics, the oil and the cellulose based paper and pressboard within a transformer. The positive charges are effectively being diffused and carried within the oil, and the negative charges are preferentially captured and absorbed by the cellulose surface of the solid insulating barrier that is formed by the internal structure of the transformer. The cellulose bonding structure is constituted by the network of strong hydrogen bonding. The negative charges would have become trapped and accumulated in cellulose when these bonds are broken, particularly during a process of degradation, whether through mechanical stress or acid hydrolysis or thermolysis, that is pyrolysis. The breakage of structural bonds has thus to create imperfection within the molecular structure of cellulose. The molecular level bond breakages, specifically at the covalent glycosidic linkages, lead to physical distortions and the formation of defects, which are the forms of structural imperfection or local disorder within the cellulose matrix. These structural imperfections would thus to disrupt the regular crystalline structure of cellulose, causing to attach new specific chemical groups to the cellulose structure, which can introduce additional localized energy levels within the material's band gaps. The localized states can capture or trap charges, that is, electrons or ions, influencing the material's electrical conductivity and overall performance, especially in applications like electrical insulation. However, specific changes in atomic structure of cellulose material and its local chemical environment would actually determine whether that deformed material will preferentially trap negative charge carriers, that is electrons, or positive charge carriers, that is ions. Such occurrence is a significant issue, particularly in case of large Forstall cooled power transformers, since the accumulation of static charges can lead to partial discharges, causing ultimately to have potential transformer failure or even fire hazards. Transformer oil's dielectric strength refers its ability to withstand electrical stress before breakdown. The presence of free charges would thus to act as charge carriers, and that results increasing the oil's electrical conductivity, which is negatively impacted on its dielectric strength. Dynamics of ionic transportation between oil and paper in operating transformers. Under the influence of the applied electric field, ions are being generated within the transformer oil, which then to migrate toward the paper interface. The porous structure of the cellulose paper would thus to allow partial penetration of these ions, causing to have some charge accumulation at the oil paper boundary. This interfacial charge transfer process has forced to alter the local electrical field distribution, influencing space charge behavior, field distortion, and long-term insulation degradation. The dynamic equilibrium between ionic drift, diffusion, and their recombination would obviously have to determine the overall dielectric performance of the composite oil paper insulation system. Ions in transformers insulating oil would have to create through the process of mechanical, thermal, and electrical stress as developed within the oil. Chemical degradation through oxidation reactions and dissolved contaminants can also be influencing factor to produce ionic species. Under an applied electric field, the movement of charged particles or ions through the insulating oil and paper is referred as the process of ion drift. Positive ions, that is cations, that are being attracted to the electrode with a negative potential, causing them to drift through the oil toward the negative surface of the paper insulation or the winding. Negative ions, that is anions, which have to originate from impurities like water molecules or from the oil's degradation over time, are being attracted and drawn towards the positive electrode, that is anode. Positive ions can also be originated from impurities in transformer oil, such as copper ions from corrosion of copper conductors, often caused by factors like oxygen, moisture, and spatially corrosive sulfur compounds. The drift velocity of an ion, that refers to its average linear velocity under an applied electric field, whereas the ionic mobility is defined as the drift velocity of an ion per unit electric field. Ion mobility has to depend on the characteristics of the ion itself, which includes ion's effective charge, its size or radius, and the viscosity of the surrounding medium. These three: effective charge, its size, that is the radius of the charges, and the viscosity of the surrounding medium. An electric field exerts an electrostatic force on charged ions. Electrostatic force F equals to ions charge, that is Q, into electric field strength E. Every charged ion creates an electric field around itself, and when another charged particle or ion enters this field, it interacts with the established field. Positive charges in the field would have to experience a force in the same direction as of the applied electric field, whereas negative charges in the field would have to experience a force in the opposite direction to the applied electric field. Therefore, a charged particle or ion in an electric field would have to experience an electrostatic force that causes the charged particle or ion to accelerate and move, either attracting it towards or repelling it from the source of the field. Ionic mobility in transformer oil paper insulation refers to the movement of ions under an electric field, a process known as ionic conduction. That is, through the process of ionic conduction, ionic mobility would have been exist within the transformer oil paper insulation system. This phenomenon contributes to charge accumulation, oil flow electrification, and can ultimately affect insulation breakdown. In transformer oil, there are three fundamental modes of charge transport. One, ion drift, which refers to the orderly movement of ions in an uniform direction due to the force exerted by an applied electric field. Number two, diffusion of ions is the random thermally driven movement of ions from areas of high concentration to low concentration zone, and it does to continue in this direction until the molecules are evenly distributed, a state known as equilibrium. And number three, electro-convection, which is a type of movement phenomenon of a dielectric fluid caused by an electric field. Ion drift, diffusion of ions, and electro-convection. These three fundamental modes of charge transport in transformer oil would have to govern the ionic migration mechanism. Dynamics of electro-convection in a dielectric fluid. Charge injection. An electric field, while it is applied to a dielectric fluid, causing free charges to be injected into it from an electrode. Coulomb force on free charges in fluids. These charges are then subject to a Coulomb force from the electric field. Fluid motion. Fluid motion caused by electric fields is a phenomenon. Fluid motion caused by electric fields is a phenomenon known as electro-hydrodynamics, that is EHD, where electric fields induce flow in fluids by applying forces to charged or polarized particles within the fluid. Hydrodynamic instability. It is a phenomenon where an applied electric field causes fluid motion, leading to convective instability even when temperature gradients are stabilizing. This instability arises from the coupling of electric fields with fluid motion in regions with conductivity gradients, which creates electric body forces that drive fluid flow. Hydrodynamic instability during electroconvection phenomenon in a dielectric fluid. coupling of electric fields with fluid motion in regions of conductivity gradients. An applied electric field, particularly at higher voltages, can induce a gradient in itself when it interacts with, with a fluid of non-uniform conductivity. Accumulation of free charges in fluid. A fluid of non-uniform conductivity must have the non-uniform current density even with a uniform electric field, because current density is directly proportional to the conductivity and electric field. Non-uniform current density can lead to charge accumulation at the boundaries between different conductivity regions. Instability in fluid motion. The interaction between the accumulated free charge and the local electric field generates a force. The interaction between the accumulated free charge and the local electric field generates a force. This force would have to accelerate the charged particles, which thus to colloid with, with neutral fluid molecules, transferring their momentum to the surrounding fluid, causing it to move and generate convection currents. This force has to create a complex flow pattern, causing hydrodynamic instability in the fluid motion. Hydrodynamic instability in transformer dielectric fluid is driven by the underneath electrical forces. 1. Coulomb force on free charges in fluid. Number 2. Polarization forces in a non-uniform electric field. These two are the primary driving forces for causing hydrodynamic instability in transformer oil while subjected to an applied electric field. However, there are other underneath factors which include: 1. Localized overheating, that is hotspot; changes in viscosity due to thermal degradation leading to sludge formation and acidic byproducts. Number 3. Acoustic or vibrational effects. Number 4. Effects of impurities, that is due to conductive particles and moisture content. Number 5. Accumulation of charged particles within the oil. Coulomb force on free charges in transformers dielectric fluid. Free charges are the mobile ions or electrons that are not bound to an atom and can move freely within a fluid. Concentration of these charges in transformer oil is typically very low under normal operating conditions, but it increases under high electrical stress, temperature, or contamination. The free charges would have to experience a Coulomb force due to the strong electric fields present between the high voltage electrodes in the transformer. In the context of transformer, the term high voltage electrodes refers to the high voltage windings and their associated terminals or bushings that provide the electrical interface between the internal transformer components and the external high voltage circuit. When a high electric field is applied, it can cause the weak chemical bonds in some molecules within the fluid to break apart, that is dissociation or dissociate, create both positive and negative ions. The Coulomb force is an electrostatic force which would have to act on free charges within the fluid, causing them to move and form convection currents. As of the fact, the Coulomb force is the most dominant force which is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. The fundamental principle of Coulomb force is thus to be clarified as the electrostatic force of attraction or repulsion that acts between two or more particles that have a net electric charge. Coulomb force is much stronger than other electrokinetic forces, and that can be defined by the Coulomb's law. Coulomb force between two charges in transformer dielectric fluid can be calculated by the underneath expression. Coulomb force between two charges F equal to 1 by 4 pi epsilon r epsilon 0 into Q1 by Q2 divided by r square, where F is the electrostatic force between 2-point charges, Q1 and Q2 are the magnitudes of the charges, r is the distance between them, epsilon 0 is the permittivity of free space, approximately 8.85 into 10 to the power minus 12 farads per meter. Epsilon r is the relative permittivity, that is dielectric constant of the transformer dielectric fluid. Coulomb force within a transformer's dielectric fluid must have to depend on factors that affect both the electric field and the dielectric properties of the fluid. In transformer dielectric fluid, the Coulomb force depends on the underneath physical properties of the fluid. 1. Coulomb force between charged particles is inversely proportional to the permittivity of the transformer oil, which is the product of the permittivity of free space, that is epsilon 0, and the oil's relative permittivity epsilon r. Hence, a higher relative permittivity or dielectric constant of the oil leads to a reduction in the Coulomb force between the charges. Number 3, in order to achieve superior insulation performance, the relative permittivity of new transformer oil typically lies in the range of 2.2 to 2.5, which is substantially higher than that of a vacuum. That is epsilon. Vacuum is called the free space, permittivity of the free space, that is epsilon 0 equals to 1. At room temperature specifically, in a range of 20 degrees centigrade to 25 degrees centigrade, the relative permittivity of moisture is approximately 81, which is rather significantly higher than that of transformer oil. Water molecules are highly polar in nature and are being strongly influenced by an electric field. Number 6, under an external electric field, these highly polar water molecules must have to experience a torque that attempts to align their dipoles with the field direction, that is applied field direction. Number 7, therefore, any such addition of highly polar water molecules in nonpolar oil that results in a mixture exhibiting significantly higher overall polarization when subjected to an external electric field compared to dry oil alone. Number 8, even if a trace of water present in transformer oil, especially in the form emulsified or free water, can also cause an increase in the relative permittivity, that is dielectric constant of the mixture. This effect is more pronounced with increased water content in oil. Number 10, as of the dilation, where it is important to note that the relative permittivity here is inversely proportional to the Coulomb force between two charges placed between it. So, higher be the relative permittivity of the mixture, that would cause to lower the Coulomb force between two charges placed within it. Existence of water molecules in transformer oil would have further to instigate certain increase in the dielectric loss factor tan delta, which is measure of the energy lost as heat when the oil water mixture is subjected to an electric field. Number 13, presence of moisture as contaminants in oil would thus to increase the overall electrical conductivity and alters its dielectric properties, leading to a weaker Coulomb force between charges and a higher risk of breakdown. Number 14, effect would have been the same while the oil is being slowly contaminated through the oxidation byproducts as produced due to dissociation of oil's chemical bonding. Number 15, dissolved gases in oil as produced due to electrical or thermal stress can form gas bubbles. These gas bubbles would have to act as conductive bridges between electrodes, thereby altering the existing electric field and the overall electrostatic forces. Let's stop here, further to be continued at later stage. Thank you for listening the video. Kindly do like, share, subscribe and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section, please. Thank you. Thank you for patient hearing.